Here's what I would like to just have you think about for a second. Let's suppose that you are an ancient mariner, and you are gonna, you want to set sail, and you're gonna go off to sea. Okay, and so I'm gonna draw a map, an incredibly accurate map of like the coast of Portugal. Okay, so here it is. Here's Portugal. I know. Some of you are like, I've been there. Here's Portugal. Okay, and here's you in your boat. And this is a top view, okay? So you have your boat like this, and here's the problem. Here's the problem, is you want to set sail, and you don't want to go to more Portugal. You've already been there. You've had your fill of Portugal. So you don't want to go north, and you don't want to go south. You want to go west. And the problem is, the wind is blowing in this direction. It's blowing toward the coast, and then it kind of curves and goes north. What do you do? Does anybody here know what you would do in this particular situation? Has anybody here ever been on a sailboat? Like an actual sailboat? Did you do any of the like rigging, jibbing and whatever? What did you do with it? There's a sail called a jib, I think. You didn't do that, did you do it?
I was 8.
You were 8, yeah. And I don't know anything about this either. Except that as somebody who is just sort of generally interested in questions like this, I've looked it up before. And I will just say, quite frankly, with no exaggeration, that the physics of what goes on here is above my head. Because it has to do with like fluid dynamics and pressure and like all this stuff that is just, it's really, the physics part of it is intense. But to put it into practice actually ends up not being that hard. People figured it out literally thousands of years ago. And it turns out that if you just have like one sail, like if this is your sail, then you're out of luck, right? If it looks like this. Because basically the only way it's gonna move is the direction that the sail is pointing if the wind is blowing into it. And that's it. But if you start adding multiple sails, if you set up multiple sails that can be adjusted separately, if you have bigger sails and smaller sails, if you have sails that are on top of each other and sails that are below each other, then what happens is you can, and I'm making this up because I don't know anything about sailing. I literally think maybe jibbing is a thing. But if you take like the lower boom sail and the upper jib sail and you set them up like this, and then you jib the rigger like this, and you stern the poop deck like that, then what you end up with is this crazy like configuration of fabric that ends up generating a force in like almost the opposite direction of the wind. Now you can't get completely the opposite direction of the wind, at least from what I understand, but you can get enough, you can like pick up enough velocity in a direction that isn't the way the wind is blowing, that if the wind is coming straight toward you, you can do what's called, I actually think this is true, I think it's called tacking. Does this ring a bell with anybody? I think it's called tacking. And basically what that is if the wind is blowing straight towards your sailboat, then you go like this, and then like this, and then like this, and then like this. So you can go at an angle to the wind, but like you can kind of like, it's blowing one way and you're going the other way. And what I love about thinking about stuff like this is that I know that if a bunch of like Greek sailors 2,000 years ago figured this out, we could figure it out too. I don't think I could. I don't think I could on my own. I don't think if you gave me a bunch of sail material and some like timbers and stuff, I don't think I would make it. But if we together were to work as a team, I think we could figure out how to make a sailboat and do stuff like this. It would take us a while, but if we knew it was possible, we could do it. And I think that kind of thing is really fun. And then the next step, of course, and it wouldn't be necessary, but it would be really interesting, the next step would be, okay, so once you've done that, how does it work? How is it that you get wind going one way and a boat going the other direction? Like, how do you pull that off? And that's where the fluid dynamics and, you know, all the different forces that are involved that are really difficult to model, all of that stuff comes into play. And I think we could do that too. I don't know if I could figure it out just by looking at a book, but I think if we all work together, we could figure it out. And the reason that I'm bringing this up is because that skill of looking at a situation, asking a question, sometimes you have a little bit of advanced knowledge, like, I know this is possible. I don't know how to do it, but I know it's possible. So we've got a little bit of information there. That skill is incredibly powerful. That is a skill you can take and you can employ that in a variety of circumstances. Academically, in terms of your career, you can, you know, like, we have problems that we need to solve in like yard work and our personal relationships. All these things are scenarios in which we have a problem, we need to solve it, but there's not necessarily a straightforward instruction manual for how to get there. We have some general principles, and we know it's possible, but we don't necessarily know exactly how to do it. And so what I ask you all to do, and I do this a lot, I've done it a whole bunch of times and I'm going to continue to do it. What I ask you all to do is spend some small amount of time just trying to figure things out on your own. And the problem that I presented to you all the other day was, how do you find the force of friction on a cart with a block of wood in front of it on a horizontal level track? How do we find out how strongly friction is pushing on this? And I said it's moving, so there was that condition. It's moving, so it's horizontal. But you mean, the way we approach this, we could probably like apply this to other scenarios as well. Once we figure out how to find an unknown force, we could apply that to a bunch of other scenarios as well. And this is kind of an interesting thing because there's some stuff you don't know. Like, for example, does the force of friction change if it goes faster or slower? I haven't told you that. So you don't know that, but you could try to find it out. That would be something you could actually find out if you set something up and could collect some data. If you need to measure forces, how do you do that? I didn't tell you how to measure forces, but I can figure it out, and if I can figure it out, I know you can, because your brains are in much better shape than mine. And so this initial situation, there is no one way to answer it. There's no, like, nobody will say, like, well, here's how you do it. It's just that there's a bunch of different ways. But here's what's really neat, is in my conversations with you and in my observations of you, I saw 3 solutions, and there was a fourth as well. The one that I'm thinking of is really reliable, and so I'm going to tell you my scenario. But before I do that, I'm going to tell you the other 3 that I saw. One of those I've seen before, and that's the scenario where you take the cart with the block in front of it, and you give it a good shove, and then you stop pushing on it. And basically what ends up happening is this. You have the cart, and it just rolls for a little bit, and then it stops. And what the group that did that was thinking is, okay, if we think about Newton's second law, there's something about forces and there's something about mass times acceleration. We can find the acceleration by using the graphical analysis program, the supercarts can tell you their acceleration. And we can find the mass if we have, like, I don't know, whatever you use to find mass. You all did that in chemistry, you use balance. So that group was like, if we can just find the mass of this, then we can maybe multiply that by the acceleration, and will that be the friction? And they actually like reasoned it all through mathematically, and they were right. This is a little complicated, and the main reason it's complicated is because there's you only get motion for a really short amount of time. So that you don't get this like consistent data to look at. It's not the worst idea in the world. In fact, it's a terrific idea. I think the way that I'm going to show you is better, but that doesn't mean you shouldn't do this, and it doesn't mean it won't work. In fact, it might work just as well. So that was one idea. Another idea, and this one I crowed about in class, so you all saw this. They had their cart set up with the block in front of it, and then behind it, they had another track with another cart on it, and that was hooked to the first cart with a rope, and they let this one just roll down the ramp, and it kind of pulled the other one along, and they adjusted the height of the ramp, and depending on what the height of that ramp was, they could get it to kind of move at a constant velocity, which was also super clever, really clever. And I've never tried this before. I don't know how well it works, but it's worth a shot. And then I was talking with a student during lunch yesterday, and she suggested, which I thought was a great idea as well, what if we use a sail? What if we make a sail on the boat, or on the cart, and then we have a fan, and we like, you know, this battery powered fan, so I can't make it actually turn because it doesn't have batteries, but like, this will work. If you use wind, you can make the cart go. And we were thinking, well, if the problem with that is that the farther the cart gets from the fan, the less force is being applied. But if we could like put the fan on one cart, and then put the sail on another cart, and then just kind of move the fan behind it, and maybe this would be a more constant source of force than if we were to push it with our hands. Because if you push with your hand, you're going to find that the force you're applying is really variable. But maybe with a fan, it's sort of buffered, because it's like the air, like if you move the fan a fraction of a meter per second faster or slower, it doesn't affect the airspeed, because it's kind of like, it's like a shock absorber almost. Anyway, so I thought the idea of a fan plus, I know, amazing, huh? Plus a sail was pretty clever. And then the only problem with this is that somehow we have to measure force. And but the supercarts have a force sensor built into them, so we were just kind of playing around with this and thinking, well, maybe it would work. And what I love is that these three groups and students came up with their own solution to the problem. And some of those solutions might very well be as good or better than the one I'm going to propose to you today. I don't want you to hear what I'm about to say and think, okay, this is the right way, this is the only way. I just want you to recognize that because I've played around with this a bunch, I have found this particular method to be pretty darn reliable. All right, so here's what we're gonna here's what I'm gonna propose to you, and if you want to try it a different way, I encourage you to do that. But we'll talk in a second about how we're going to kind of verify and validate the data that we get. So it may be you do it a different way and get good data, but you'll know, because we're going to talk about the data, and you'll know whether yours is decent or not. All right, so here's our big question. What is the size of the force of friction acting on a moving cart and block system as it rolls along a track? Friction is a force. It's a push or a pull. Like all forces, it's measured in the metric system in newtons. So how hard is friction pushing on something? I can tell friction is pushing on this. I can feel it. It's not pushing very hard though. So I know I don't have to push very hard at all to get this to move. I know that the force of friction is going to be pretty small. We'll talk about that in a second though, because it's kind of interesting. The first thing that I suggested to you is that this is not something where there is one number that we can find with a great degree of precision. Like, it is not, we're not going to get a number like 1.68423 newtons. There's going to be a lot of variability. What we really want is a range. If we do our job well, that range will be relatively small, and then within that range we kind of like to know what the average is, so that we can have a number that we use. Maybe we end up using 3 newtons, but we know that, you know, in our tests it varied between 2.5 and 3.5. That would be a reasonable, I don't, you know, that's a reasonable way to express the amount of friction acting on this car. Between 2.5 and 3.5 newtons with an average of about 3. That is a perfectly reasonable way to describe what we're talking about here. What will that number be? Well, that's kind of interesting because we're measuring it in newtons. And how are you going to know if you're getting good data? Like, I told you that the force of friction isn't very big. I can feel that it's not very big. But I also know that I don't know how much a newton is. I was talking with the other class, and there's this box of books here. It's kind of heavy. If I picked it up right now, like, it's got some funk to it. I can tell you, like, just picking this up, this is like, I don't know, I would say, my guess, 7 pounds. It's like 7 to 10 pounds. I don't know. It could be more, it could be a little less, but it's not dramatically more. Like, I know, since I can pick this up, I know it's not 100 pounds or 200 pounds. I also know, since it thunks, it's not like half a pound. Like, this to me feels like, I don't know, 10 pounds. Maybe, I don't know, 10 pounds. I just don't know. But if you were to measure the weight of this object and tell me it's 10.5 pounds, I'd be like, that sounds right. If you were to say it's 8 pounds, I'd say that sounds right. If you were to say it's 13 pounds, I'd say that sounds right. If you were to say it's 38 pounds, I would say, I don't think so. Right? Because I know that I can't pick up 38 pounds with just my fingertips. I know that, like that's heavy. So it's not 38 pounds. I think it's more than 10. Like, the more I pick it up, the more I think it's, but this is 15. I mean, it's just like come right out and say it's 15. So what about newtons though? Like I can tell you that this is, I'm pushing right here with less than a pound of force. Like, that's hardly anything. But how many newtons is that? We don't really know. And I don't even really know. If this weighs 15 pounds, then I have to do a bunch of math in my head to get it to newtons. There's about 4.5 newtons per pound. So that would mean, if this is 15, that would mean it's like 75 newtons. And that makes sense to me because I know that a person is like somewhere between 600 and 800 newtons, you know. And so if this is like that 10th, roughly the weight of this is like a person divided by 10, so I don't know. I mean, all of those are real rough. But if you are collecting data and it tells you something about force when you're pushing your cart and you get like 3.6 newtons, is that right? If you get 0.08 newtons, is that right? You don't know. There's only one way you're going to know if you're getting good data, and that's by comparing it with what other people are getting. You have to communicate. Don't assume your numbers are right, and you'll see in a second there's a trick to the way that this, not trick, but there's some technique to the way that you are going to collect this data, and you can't just write down the numbers if you get it. It won't work, okay? And our operating assumption for this is going to be that if we have the cart on a horizontal track, and then there's at a minimum, and it's moving, then at a minimum there's going to be 3 forces acting on it. Okay, it's got weight. The force of gravity is pulling down on the object, and that we could find if we knew the mass of the cart in a block of wood. We could multiply that by g, which which is 9.8 meters per second squared. It's an acceleration. And that would give us the amount of force that gravity is pulling down on this cart and block with. And then since it's not accelerating down, it's not falling, that must mean that whatever force is pushing up on it is equal to that. And that upward force, you could call it the force from the track, but typically when we have something resting on a surface and it's being supported by the surface, even just partially, we call it the normal force. The direction of that force is perpendicular to the surface itself. A horizontal track, perpendicular, is going to be straight up. So we have one straight up force, one straight down force. These two forces, we can reason, are going to be equal and opposite because nothing's happening to my cart. It's just sitting there. It's not going down, it's not going up. Things that are motionless are not being affected by an overall force. And in this direction, there doesn't appear to be an overall force. That's a reasonable thing for us to just kind of conclude. And we'll build the math in next week. And then the other piece is, well, if it's moving, we know that friction opposes the motion of a moving object. It always does. So if it's moving this way, then friction is pushing this way, the exact opposite of the direction that it's moving. If, like one of the groups yesterday, there's nothing else pushing or pulling on it, then those are the only three forces acting on it, and there will be an overall force in the direction of friction. But what I'm proposing is that a really good way to set up our investigation here is to create another force on this cart and block and make that force the same size as friction. How will we know that it's the same size as friction? Because if these two forces are equal, then there will be no overall force in the direction of its motion, which means it will have no acceleration, it will have a constant velocity. It's in what we call dynamic equilibrium, and the sum of the forces will be zero. There will be no overall force. All we need to do is look, somehow make a measurement of acceleration or velocity to see, is the acceleration zero? Is the velocity constant? If that's the case, then these two forces have to be equal in magnitude. So if we could measure this somehow, we could like push or pull on our cart in the direction of its motion like this and get it to move with a constant velocity. If we could measure that force that we're applying, that will be the same as the friction force. It would be the opposite direction, but it would be the same magnitude. And that's what I would recommend that you do, because it turns out that this business of making it move at a constant velocity isn't really that hard. It ends up not, it's just not that difficult. I was just playing around yesterday and I got it to work, and I'll show you what my setup is. And this is what I would recommend that you do as well. We've got all this equipment. So it starts with a supercart, brand supercart. And these now all have handy little hooks on them. On one side of the cart is a spring. This provides a pushing force, but this doesn't actually measure anything. There's no measurement here. On the other side is a hook. It doesn't seem to move, but as it turns out, this hook is connected to an internal force sensor. And it doesn't seem to move, but it is just a little tiny bit. And if I pull it out, it will measure the pulling force and give me a positive number. If I push it in, it will measure a pushing force and give me a negative number. So if I hook like a string or something onto this and pull on it with a constant force, then I can measure that force by using the built-in force sensor. And so I'm going to load graphical analysis and kind of walk you through this process. This is something that it takes a little practice to do this, but everybody needs to be able to. So you should all watch, and you should all think, and then also recognize that you're not all going to remember. So rely on each other to do this. Okay, so it starts with turning the cart on, which it is, blinking. I click sensor data collection. It's going to find this cart. My new glasses, I can see. So that's this cart, and then here's where it starts to get, like, you have to remember this. So watch what I'm doing so that you can do this yourself. it will not automatically be set up to record force. It won't do it. So I have to click this little down arrow and add force to my list of sensor channels. Position will allow the computer to calculate velocity and acceleration. I don't need any of these acceleration. These are built-in accelerometers, and they're really precise, but they also are like, there's going to be a lot of noise. They're not great for what we are doing. But the position sensor uses calculus, and basically it's the same system that we use for tracker. And it can calculate acceleration or velocity. And now we've got force checked as well. So now this is going to tell us positions. I can see, you probably can't, but I can see down here it says position 0.134. If I turn this dial, that position changes. Right? I'm making it think it's moving around. And this has force, negative 0.4. That seems to indicate that there's a pushing force of about 0.4 newtons on the force sensor, but that's weird because there is no pushing force on it right now. There's nothing pushing on it, in fact. If I pull on it, I can see, now it's like 10. If I push on it, I can see it looks like it's like, that's like 14. But if I just don't do anything, it tells me 0.4 about newtons this way, and that doesn't seem to make any sense because there shouldn't be anything pushing or pulling on this. So one of the things that we have to do is we have to tell it, by the way, this is what 0 newtons feels like, just so you know. It doesn't know that. It's just using voltage, basically. And so there's some voltage, and it's like, well, I don't know how many newtons that is. It seems pretty small. I'm gonna guess it's 0.37. You're wrong. It's not 0.37, it's 0. And I'm gonna tell you that it's 0 by clicking on this button right here and pushing this button that says 0. And now it's like, oh, okay, fine, 0. So now it's reporting 0, and if I push on it, now it's telling me the actual size of my pushing force, about 4. Or if I pull on it, it's telling me my pulling force of about 4 again. And when I let go, it's back to 0. You can actually like mess with your brain by doing something like this. Right? Now it's telling me it's pushing down with about 1/10 of a newton. What's going on there? This thing, it's the weight of this thing. Now it's going to be like plus 0.1 newtons. But if it's horizontal, it should be 0 or really close to 0. Okay? So I've got this set up, and the next thing, and again, like I'm showing you this, it's going to be on the video. Not all of you are going to remember this, but enough of you should remember this that you can help each other, so that it doesn't have to just be me, like one-on-one helping everybody with this in the next 20 minutes. Otherwise, it'll just take forever. But we only need 2 graphs. One graph should show force. The other, you could pick position, velocity, or acceleration. You should be able to use any of those graphs to determine if the object is accelerating. I like to use velocity. When I look at a velocity versus time graph, I can generally get a pretty good sense of whether an object is accelerating or not. Now here's the problem. If I collect data now, and I try to just like pull on my force sensor, I can't do it because I'm shaky, then you can see like, wow, my force is really wobbly. Like that's not easy. But you know what does pull with a really constant force? Is gravity. So if I take an object and I took my Gigal and put a battery in it, and then I just hooked it over a pulley on the track, and it turns out that this ended up providing just about the right amount of force for it to move at a reasonably constant velocity. This string isn't very long, so one of the things that you're going to see is that my graph and my resulting data isn't great. You all can do better. Okay, but I'm gonna just make it. How am I gonna do this with this? I'm just gonna do this anyway, and so you'll at least see what it would look like. Okay, so and you'll get better data because you can use a longer string. You'll just have a little bit more time to get data from your graphs, and you're gonna have 2 people, so you're not gonna have to be running back and forth like I am. But this is effectively what you're gonna do, okay? So, so you can see it's sped up, and that's normal. But there was a time here toward the end where it sort of stopped accelerating. Like this little section right here, if I were to zoom in on that using the zoom in button, so that's from about 2.3 to 2.8 seconds. That's like a half a second. When I zoom in on that, my speed is varying from 0.26 to less than 0.29. So that's pretty small. That's like, roughly a 10% variation in speed. That's not perfectly constant velocity, but it's close. You can do better, but this is reasonably close. That's from 2.3 to 2.8 seconds. So if I look at my force during that time, what it looks like is it's about 0.43 newtons. That means that my applied force, my pulling force, was about 0.43. Wasn't moving at exactly a constant velocity. I could do better, but without spending a ton of time running this over and over, I could say, well, it was approximately a constant velocity. And at approximately a constant velocity, the force of friction should be approximately equal to the magnitude of that applied force. So it looks like the force of friction here was about 0.43. When I did it this morning with a different cart, it was 0.35, and it moved at a constant velocity. I don't know what's different. I mean, students were messing around with it. It might be just a different piece of wood. Maybe this has been done like 20 times, and it's like kind of smoothed out the wood, or it's smoothed out the track a little bit. So maybe the force of friction actually did decrease. I don't know. I do know that if I wanted to do this again, I would do two things. One is I'd probably put a little bit less weight on here, so I'd probably take the battery off, and I don't know, I would just start like this actually. I'm going to take the battery off and just see what happens with no battery. Oh, it doesn't even move. Hang on. Let's try it again. Yeah, it slows down. That's not enough. That wasn't enough force. So you can see that's dramatic acceleration. I don't know that I would trust that, but I mean, if we look here, we can see it's much less force. That was like 0.27. So somewhere between 0.27 and 0.45. So I don't know. I'd put something else on there and see. There are a bunch of things that you can play around with in the back of the classroom. These little hanging weights, these little hooks that you can use. There's string, there's pulleys. You have the carts. What I want you to do is tackle this big question of what is the range and the average force of friction acting on these carts. If we can figure that out, we can use that to figure out what I am going to refer to for now as the stickiness, the degree to which the cart and the wood are kind of being resisted by the track itself. It's a kind of a fundamental property of friction. We'll start calling it the coefficient of friction down the road, but for now, just think of it as stickiness. And that's really what your job is, to try to figure that out, okay? And ideally, you'd be working in teams, but also verifying your data with other groups, with me, with Ms. Adams, with other groups, so that as you start to collect data, you're confident that it's good data, because that's the only way we're gonna know. But I mean, at a glance, I'm thinking 0.3-ish seems like 0.3, 0.35, like if you're getting numbers that are dramatically different from that, you're probably making a mistake. Okay. All right, does anybody have any questions before you get started? All right, let's see what you come up with.